Hello everyone, I'm Dong, from University of Science and Technology of China. We propose E²SL, the efficient depth sensing from event-based structured light. Structured light is a popular 3D imaging technology. It consists of a camera and a projector. By projecting design patterns onto the scene and capturing the reflected pattern, geometric information is obtained through decoding. After obtaining the geometric information, we can enable applications such as projection mapping. The key lies in establishing correspondence through temporal decoding, such as the temporal coding gray code. However, these encoded patterns are often time-consuming to project and capture. Therefore, many approaches based on spatial coding patterns have been proposed, enabling faster encoding and acquisition. Meanwhile, with the growing adoption of event cameras in various fields due to their high temporal resolution, introducing event cameras into structured light systems enables high-speed 3D reconstruction. However, traditional depth decoding methods often suffer from low accuracy. Although learning-based approaches have achieved significant improvements in accuracy, they typically come at the cost of slower inference speed. To address these challenges, we propose an efficient event-based structured light depth sensing network that runs at 7.7 milliseconds per frame while achieving state-of-the-art accuracy. In addition, we introduce a scalable event-based SL simulator for large-scale synthetic data generation. We further establish a real-world benchmark with high-precision ground truth, demonstrating the superior performance of our method in complex scenarios. Frame-based structured light can be categorized into temporal encoding and spatial encoding techniques. Typical examples include gray code and phase-shifting methods. However, these approaches often require projecting multiple patterns, which makes the acquisition process time-consuming. To address this limitation, spatial coding techniques that exploit spatial information such as color-based encoding have been proposed. These methods can significantly reduce the number of projected patterns. However, color-based approaches are highly sensitive to object surface properties and ambient illumination, which can degrade reconstruction accuracy. To address this issue, speckle patterns are introduced and have even been adopted in commercial systems. However, their reconstruction accuracy remains unsatisfactory. With the advancement of deep learning, learning-based methods have further improved accuracy, but they often suffer from slow inference speed. Meanwhile, the emergence of event cameras has further advanced structured light technology. By introducing event cameras into structured light systems, high-speed 3D reconstruction can be achieved, leveraging their superior temporal resolution. In addition, the high dynamic range of event cameras further enhances the performance of structured light systems, enabling more robust reconstruction under challenging lighting conditions. To achieve efficient event-based structured light depth sensing, we first build a real-world event-based structured light system, which consists of a high-speed projector and an event camera. To enable the training of learning-based methods, we also develop an event-based structured light simulator. We first capture calibration data to perform system calibration and epipolar rectification. After rectification, the projected pattern is also rectified accordingly. The rectification parameters and the rectified patterns are then loaded into a frame-based structured light simulator, which renders the corresponding intensity frame, depth, and mask. To simulate the imaging process of the event camera, we alternately turn the projector on and off. When the speckle pattern is projected, an structured light frame is captured. When the projector is off, an ambient frame is recorded. The logarithmic intensity difference at each pixel is then computed between these two consecutive frames. Following the imaging principle of event cameras, events are triggered whenever the logarithmic intensity change at a pixel exceeds a predefined threshold. To facilitate subsequent processing, the raw event stream is integrated into a binary event frame by accumulating the events generated between the projector on and projector off intervals. Subsequently, the E²SL network decodes the binary event frames to recover the geometric information. Next, we provide a detailed description of the decoding process of the E2SL network. For the E2SL network, the binary event frame is first processed by the binary embedding lookup table module. The module operates in 3 stages. First, a CNN is trained to map each k times k binary patch to a feature vector. Then, the trained network is used to enumerate all possible binary patch inputs and cache their corresponding outputs into a lookup table. Finally, during inference, feature extraction is performed efficiently by directly indexing the LUT with the input patch, thereby avoiding costly network computations. Since the binary embedding lookup table cannot effectively capture sufficient contextual information, we introduce a spatial context enhancement module to model long-range spatial dependencies. Specifically, the module applies wide context convolution on downsampled low-resolution features to enlarge the receptive field efficiently. The features are then upsampled using nearest neighbor interpolation to maintain computational efficiency. After obtaining the extracted feature maps, we perform depth estimation using geometric prior regression. Specifically, the feature of each pixel is processed by hierarchical MLPs with 3 successive one-hot decision stages, followed by a final regression stage. We set the network output range from A to B, which is progressively discretized in a coarse-defined manner. It is first divided into C1 coarse classes, then each class is further split into C2 subclasses, and finally refined into C3 finer classes, resulting in C equals C1 times C2 times C3 discrete intervals. Finally, a regression MLP is then applied to produce the final refined depth value. To accelerate the estimation process while maintaining accuracy, we leverage geometric priors to effectively constrain the output range. To validate the effectiveness of our method, we conduct comprehensive comparisons with various depth estimation approaches in static scenes, including both traditional and learning-based methods, on synthetic and real-world datasets. The synthetic dataset is generated using our self-developed data synthesis pipeline, while the real-world test set is collected using our custom-built event-based structured light system. The ground truth is obtained using a high-precision 3D scanner. For the evaluation metric, we report the outlier ratio under different disparity thresholds, the depth RMSE, and the network inference time, which is presented as latency. The results demonstrate that our method achieves state-of-the-art accuracy while maintaining very fast inference speed. We present qualitative visualization results on the synthetic dataset, including the disparity maps and corresponding error maps of different methods. The qualitative evaluations show that, compared with ASN and CTD, although they produce more complete disparity maps, they tend to lose fine details and perform worse under strict outlier ratio thresholds. In contrast, compared with SGBM and GD, while those methods preserve comparable fine details, our method generates more complete and consistent disparity maps. We also present qualitative visualization results on the real-world dataset. The results exhibit the same trends observed on the synthetic dataset. Beyond static scene evaluation, we also conduct experiments in dynamic scenarios. Specifically, we use our real-world event-based structured light system to capture various dynamic scenes at 100 fps that we compare SGBM and our method, as these are the 2 fastest approaches in terms of inference speed. The qualitative results demonstrate that our method produces point clouds with better structural integrity. We further provide additional results in dynamic scenarios, including challenging cases such as metal material scenes and high contrast scenes. We further compare our system with various sensors. We present point cloud reconstruction results obtained with different sensors. The results further verify the superiority of our method and system. In summary, we propose an efficient event-based structured light depth sensing network that runs at 7.7 milliseconds per frame while achieving state-of-the-art accuracy. In addition, we introduce a scalable event-based SL simulator for large-scale synthetic data generation. We further establish a real-world benchmark with high-precision ground truth, demonstrating the superior performance of our method in complex scenarios. Thank you for listening.